A piece of junk. Oh, it actually did it. How about that?
You're muted.
See, I told you I'm not muted. Oh God. Would it be inappropriate to swear over Zoom? All right, now you should be able to hear me, I think. All right, 4 people in the waiting room. All right, I'm just gonna get going here. So your graph should look like this. All right, so you should have your axes labeled, right? It looks kind of small there. Maybe I can get a little bit bigger. Ln of K, 1 over T in Kelvin, right? We want 1 over temperature on the x-axis, ln of K on the y, and obviously give it a title. And you're going to need to find your slope. Okay. Why do we need to find the slope? Because the slope tells us the activation energy. So my slope there is 23,777 negative. Okay, so you can attach your graph as a separate attachment, or you can sketch it, or you can embed it. There are many options for you, but and if you don't know how to graph, let me know. Office hours, we had office hours this morning. Nobody showed up. I'll have office hours Tuesday morning, 8 to 10. Hopefully you show up if you don't know what you're doing. Because when's the lab due? Wednesday morning. Okay, so, and again, you can email me over the weekend. That's fine too. So, but don't wait till Tuesday night, right? That's too late. Do not wait. Any questions before I switch over to the iPad about?
I have a quick question.
Go for it.
So for like the equation, the y equals mx plus b, but like in the chemistry form, what do we put for ln of a?
We don't care about ln of a.
Okay, so just eliminate that from the equation.
So let's see if I can make this bigger here. So you can see my screen. You can see the ln of a is the y-intercept. 3.31365 is equal to the ln of a. If we were interested in finding out the Arrhenius factor, then we would look at that. But we're not interested in the Arrhenius factor. We're only interested in my slope, because the slope is what we're learning, what we need to find the activation energy. Okay.
Got it. Thank you.
And yes, I will change the due date. The lab is not due today. Okay, so I'm going to switch over to the iPad. Those are the raw scores, so they haven't been, I'm still grading them. So the question was, are those, the grades in Canvas are always the raw score before the curve. So because you asked this question, I'm going to just review it with you. So if you go back in your chapter 12 notes, you'll see that the rate constant is equal to Z times P to the exponential of EA over RT. P is the Z is the collision frequency, and P is the steric value. Another way you could think of this is the effective collisions. Remember when I said in order for something to react, first of all, they got to collide. But they have to collide with the right energy. That's where activation energy comes in. And you have to collide from the right angle. You know, I said the example of you're going to ask somebody out, approach them face to face. That will be an effective collision. If you sneak up from behind somebody and say, hey, will you go to prom with me? No, that's not going to work. All right. It will not be an effective collision and you'll probably get arrested. So this is how many times you bump into the person that's approaching them from the correct direction. Okay. Z times P is sometimes called the Arrhenius factor. So the equation becomes this. And then what we did is we took the ln of both sides. And that's what we got by taking the ln of both sides, rearrange it. And there we go. We have the 1-point form of the Arrhenius equation. And that's what we were graphing. So Tyler said, what about the y-intercept? Well, y is ln of k, x is 1 over t, slope is negative EA over r. And so my y-intercept is going to be the ln of a. So if we were interested in finding out what the Arrhenius factor was, we would take, in this case, my y-intercept was this. So I could find the Arrhenius factor. But the lab does not ask you to find the Arrhenius factor. The lab asks you to find the activation energy. And my graph, my slope was negative 2377. So then I'm plugging in negative 2377. Now, which R value do I use? Because R can be one of two values. So anybody know which R value we should use in this equation? (8.31). And the reason why you use the 8.31 is because the units on 8.31 are joules per mole Kelvin. Okay. All right. So I know in the lab it asks you to calculate activation energy, so you can calculate it. I'm going to give you the theoretical. And we'll see how close we come to the real one. The real activation energy. You ready for this, Manly? You excited? (24.7 kilojoules per mole is the actual activation energy. Okay. So you'll need that to do your percent error. So my last question then, Lucia, is when are you going to start working on your lab?
Tonight.
Exactly. Avery, when are you going to start working on your lab? Avery, I'm talking to you. Tonight. Oh, you can unmute yourself. We like hearing your voice. So yes, work on your lab tonight. You can't talk. Uh-oh. Abducted by aliens? You're at a hotel for a swim meet. You got school going on. No, that's not cool. This is school. All right. So let's go. Let's start on chapter 14. You did watch the lecture on salts. So I'm going to pick up from there. So, like I said, chapters 14, 15, and 16 are all equilibrium. It's just variations on a theme. Okay. We went through the definitions of acids and bases in the video. Actually, it's probably, no, I don't think we did. Wait, yeah, I did. I just want to make sure. That we covered that. Salt will make the solution. Okay. Wait. This is true. Oh, solution basic. This did not cover Lewis acids and Lewis bases. Okay. So what's going to happen here? Okay. So I just wanted to make sure that I knew where. So definition of an acid and a base. There are three definitions. The first one is the Arrhenius definition. He was a Swedish guy. Okay. So this is the definition that is the easiest to understand, but it is incomplete. So it's not wrong. It's just that it's like saying freshmen are high school students. That's true, right? But you're leaving out sophomores, juniors, and seniors. But it is true that freshmen are high school students. So the Arrhenius definition of an acid is something that produces H plus. And let's go ahead and just take our nice strong acid example. Hydrochloric acid will give me H plus and CO minus. Definition of base is produces OH minus. So if we take our strong bases, sodium hydroxide produces Na plus and OH minus. Now that's a good, it's a nice, easy way to help yourself identify what's an acid and what's a base. But it's not really being very true about what's going on. The Bronsted Lowry definition is a better definition of an acid. And the Bronsted Lowry definition is that the acid is a proton donor. So an H plus is basically a proton. The reason why this top reaction isn't very good is because it gives you the idea or the thought that the HCl is just breaking apart. And the HCl is not just breaking apart. What's happening is the hydrochloric acid reacts with water. And remember that oxygen has two lone pair of electrons. Electrons like positive things. So the HCl is donating the H plus, and that's what happens. Actually, HCl is a gas. You make hydrochloric acid by bubbling hydrochloric gas through water, and then you get hydrochloric acid. So I'm just going to draw the structure of H3o plus because it's important to understand what's going on here. So you've got your oxygen in the middle. It's got 6 valence electrons. One hydrogen is bonded, one hydrogen is bonded. And then the third hydrogen, it's a proton, right? It's H plus. It doesn't bring any electrons with it. So this oxygen is donating both of the electrons. This is called the hydronium ion. So never, ever, Kiera, at any moment, is there actually an H plus floating around in the water. The H plus is always bonded to water. So that's why it's a better definition, because it actually explains more what's going on, okay? The chloride, yeah, that is floating around the water, all right? But the H plus is not. A base is a proton acceptor. That doesn't look like the right way to write accept. I guess it's right. 2 C's. So if we use these two definitions up in this example, water is accepting the proton, so it's a base. Water is accepting the proton, it's a base. Who's donating the proton? HCl. so it's an acid. How about I could do this one. So in this case, who's donating the proton now? Think of a proton as H plus. The water is donating the proton. So the water is acting like an acid here. It's donating the proton. Who's accepting the proton? Carbonate. So it's acting like a base. So water can act like an acid. It can act like a base. It can be both. There are very few substances that can act as both an acid and a base. Water is one of them. So we call it amphoteric, meaning can act as an acid or base. My drinking problem. So the reason why I put the double arrows here is because this reaction can be reversed, okay? Why didn't I put the double arrow up here? Well, technically I should, because in theory, all reactions can be reversed. However, remember when I said sometimes they'll like write the arrows to show like this reaction is such a strong forward reaction and the reverse is so small that for all intents and purposes, it's a one-way reaction, okay? It's not going to go back the other way for all practical purposes. So that's why we draw a one-way arrow. But for this one down here, yes, the HCO3 and the OH can combine. Now I feel like I got to start using the correct names for these things for you guys. Get them in your head. This is bicarbonate. This is a hydroxide ion. So when I use these words, you should have it in your mind what they are. All right, hydroxide, bicarbonate. Now, if I'm going this direction, because the reactions are reversible, in this case, OH is going to react with HCO3. The hydroxide is going to react with the bicarbonate. What's happening when you're going in the reverse direction? Who is donating the proton now? Who's donating the proton? Let's see, who should we pick on in the studio audience? Who's donating the proton, Zoe?
The bicarbonate?
Yes. So in the reverse reaction, the H is going back to the OH. So if you're donating the proton, you are an acid. If you're accepting it, you are a base. let's just do one more example here. Let's do another. Well, let's just stick with carbonate. HCO3 is a weak acid, right? You've got the 7 strong acids memorized. And if you don't have the 7 strong acids memorized, don't tell me. I don't want to know. But in case you don't know the 7 strong acids, here they are. H2SO4, HNO3, HCl, HBr, HI, and let's see, oh, perchloric and chloric. Those are the 7 strong acids. So you should have those memorized by now. That was like one of our very first unit, semester 1. That was with Mr. Nelson. So memorize those 7 acids. You need to know the strong acids because those are the 7 that break apart 100%. All other acids just break apart a little bit. So in other words, these 7 strong acids will always be a one-way reaction, okay? All other acids, you should be drawing the double arrow. So in this case, there's my acid, there's my base. The H is going to bond with the water, and then I'll end up with this. Well, this is a good one to do. I'm proud of myself. How you doing there, Mr. Lee? So instead of just writing like for the reverse reaction, whatever, so the water's the base, okay? The easiest way to do the other side is whatever the water becomes, it becomes the conjugate acid. So it's kind of like opposites. So if it's a base on this side, on the other side, it's going to be an acid. Call it the conjugate because it's paired, it's matching. So water on the left side is a base, on the right side, it's pairing acid. So then what would this be? Acid or a base? If on that side it's an acid, Ari, what's it going to be on this side? What's going to be there, Ari? Is HCO3 going to be an acid or a base? Are you there, Ari? So I can't wait around. Acid, this is going to be base, conjugate. So if you'll notice up here, what was HCO3 up here? Acid. What was it down here? Base. So for those of you who want to go on in medicine, understanding acid-base systems is crucial because your body is just one big acid-base reaction going on. And I don't know if you paid attention in biology, but how does your body carry carbon dioxide out of its system? Actually, I should go up here. So you breathe out carbon dioxide, right? The carbon dioxide reacts with water. Actually, you don't breathe out carbon dioxide. Well, you do, but your mitochondria make carbon dioxide. Carbon dioxide reacts with water to produce that. So that starts it off. Your blood takes the carbon dioxide out of your cells in the form of bicarbonate. If we look at your blood, there's very little dissolved carbon dioxide. Okay, there's not very much You know, you're not like a soda. You know, when you cut yourself, it doesn't go psh, and carbon dioxide comes bubbling out of your blood. That'd be cool if it did, but it doesn't. The carbon dioxide is HCO3. And so your body can reverse it very easily. It can turn it into bicarbonate, and then it can reverse it and turn it back into CO2 when it gets to your lungs. Okay. And because bicarbonate is both an acid and a base, your blood should stay at a constant pH, because just like water, it's amphoteric. So bicarbonate buffers your blood. In other words, keeps it at a stable pH. Okay. So if you ever watch medical shows and they're like, got to check their bicarbs, they're checking the amount of HCO3 in your blood. And if the amount of HCO3 in your blood is high, it means your body's not clearing the carbon dioxide out. And if it gets too high, we know Le Chatelier's principle. If I have a lot of this, which direction is the reaction going to shift? Towards the reactants or towards the products? If you have lots of this, the reaction is going to shift this way. What's going to happen to your blood? It's going to become acidic. Your blood should be slightly basic at a pH of 7.2. Once the pH gets to 6.8, you go unconscious and you die. So keep breathing, right? All right, so that's the Bronsted-Lowry definition. And for homework, you're going to have to identify acid base and conjugate acid and conjugate base. All right. We'll hold off on those. Yeah, okay. All right. General form of an acid-base reaction. So that's the general form of any acid-base reaction. And that's what we're going to be doing. Okay. So many times I won't actually write out the whole acid. I'll just write HA. They're all aqueous except for H2O, which is a liquid. So let's do the equilibrium expression. Products over reactants. Why didn't I include the H2O in there? Because water is a liquid, right? You don't include liquids or solids in the expression. Now I'm going to give it a little subscript here, Ka, because it's an acid problem. It's no different than what we've been doing. Okay. The subscript just gives it a little bit more information. All right. This is also called the dissociation constant. But it's just an equilibrium constant. It gives us an idea of how much of the acid is breaking apart. So now we're able to actually quantify strong acids. Strong acids have a Ka greater than 1. So if you have a Ka greater than 1, you are a strong acid. If your Ka is less than 1, you are a weak acid. All right, let's maybe do a problem. Okay, yeah, we can do that. We have time. Okay. Calculate pH of, I don't know, let's say 0.01 molar acetic acid. So calculate the pH of a 0.01 molar acetic acid solution. So this is a classic problem. This is one of the classics, Calder. I hope you enjoy this one as much as I will. So the first thing you got to do is write the reaction. Is this a strong or a weak acid, Kaya?
Would it be weak?
It's a weak acid, right? So you got to have those 7 memorized, okay? What we'll find with these problems, every problem is individual. I can't say like, oh, this is what you always do. There are some guiding principles. First thing you do is ask yourself, is it strong or weak? And once we get through all this, I'll come up with an algorithm for you, like questions to ask yourself. But there's no set way to do every single problem. So first of all, it's a weak acid, okay? So if it's a weak acid, we know that the reaction is reversible. And then we're going to write our ice table. Initial, change, equilibrium. So my initial concentration is 0.100 molar. None of this, none of this. So if I have 0 products, Kiera, I know I'm going to shift to the right. So at equilibrium, my concentration will be that. So my equilibrium expression will be Ka is equal to x squared or 0.01 x. Because it's, I never wrote out the expression. I should just write out the expression. This is what I mean by writing out the general expression. Instead of writing out HC2, H3O2, it's just easier to write A minus. So if each of these are X, you plug them in, you're going to have X squared on the top. Now, you have to look up the Ka. And there's a table in your book on page on page 658. And I'm going to give you a better table than the one on page 658, but there's a table on page 658, and the Ka for acetic acid is 1.8 times 10 to the negative fifth. Now remember what I said about X. If my molarity and my Ka are off by a factor of 100, I can assume the X is too small. So this X is going to be too small to matter, which will then make my math easier. Solve for X. So X comes out to be 4.24 times 10 to the negative fourth molar. Do not be afraid of really small numbers in chapters 14 and 15. When we're talking about acid-base systems, molarities are quite small. So that is the molarity of my H3o plus. Now, how do you calculate pH? pH stands for the power of hydrogen. It's a logarithmic scale base 10. The equation we use for pH is negative log concentration of H plus. Now remember, H3O plus is the concentration of H plus because technically H plus does not exist. It's always bonded with the water. So the pH would be 3.37 is the pH. So pretty acidic. You know, the pH scale goes from 1 to 14. 7 is neutral. That's basic. That's acidic. So pretty, that's about the strength of stomach acid. So a 0.01 molar solution of acetic acid is as strong as stomach acid. So what questions do you have so far? By the way, Tyler, you know, our body is based on water, H2O, it's amphoteric. Oxygen is in the same family as sulfur. So if you've ever watched the Alien movies, Alien, their body systems are based on H2S. There are some bacteria that function on H2S instead of H2O, so it's not too crazy. There are some bacteria that use H2S instead of H2O. H2S is not amphoteric. H2S is acidic. So therefore, some bacteria, their internal environments are acidic. And in the movie Alien, since their body is based on H2S, their blood is acidic. That's why when you shoot one of them and the acid, their blood comes shooting out, it burns you. So just be careful when you shoot an alien, their blood is acidic. And so I dare any of you to say you've never learned anything practical in my class. Now you know to wear gloves when you shoot an alien. All right, so that's how you do it for a weak acid. How do you do it for a strong acid? Strong acids are a lot easier. So let's do the exact same problem, but let's do it for a 0.010 molar solution of HCl. Oh, I don't know. Aren't xenomorphs bulletproof? That's a good question, Calder, because they do have silicon exoskeletons. So yeah, it may not work. We'll have to somehow break the silicon exoskeleton because we are carbon-based. Aliens are silicon-based. Carbon and silicon are in the same family, so their bodies will be more glass-like on the outside. So, darn aliens. All right, so for a strong acid, is it reversible? No. I think Ian heavy guns might be the only thing that work on them. Oh, and spitting blood to get you, that's just a plot flaw because you can't spit blood. You know, you spit saliva. So they need acidic saliva. It always bothered me. You know, plot flaw in the movies. I suppose they could have acidic saliva. So if my initial concentration is 0.001 molar, and I've got 0 of this and 0 of this. Oops. We really don't do an equilibrium problem for this because the reaction goes to completion. Instead of doing an ice table, don't write this down. If we did an ice table, this would be our answer because all of this reacts. Okay, all of it reacts. It's a one-way reaction. So we really don't do an ice table. What's probably more appropriate to write is I call them before and after tables. Before, after. Since all of it reacts, you know what the concentrations will be after the reaction. So this is where, you know, like I said, the first thing you have to ask yourself, Kaya, is the acid strong or weak? If it's weak, you do an ice table. If it's strong, you do a before and after table. So I already know the concentration of H3o plus. So my pH is going to be negative log 0.0100 molar. You know, this is the most comments in the chat room all year. By the way, you guys are awesome. Maybe I need to do a lecture on how you defeat an alien. All right. So negative log of 0.01. By the way, on the AP test, they expect you to do this in your head. For the multiple choice part, you should be able to do the log of 0.01 in your head, because what will it be? One, two spots, right? It would be pH of 2, because there's a negative sign out in front. Because this is 10 to the negative second, right? So if you're taking the log of 10 to the negative second, you just bring that baby down front. So they'll, when they're on the multiple choice section, they'll be sure to give you a molarity that is like 1. So if you're taking the log of 10 to the negative 4th, you know it's a pH of 4, okay? So now we can do some homework. Isn't that exciting? And everything we just did with acids, we can do with bases. But we're not going to do them yet. We're going to wait till you get really good with acids, and then we're going to do bases. My guess, honestly, is this is the last chapter we'll get through. Because this is, again, it's a tough chapter. So for homework, all right, Lucio, how about 35? You like that one? All right, let's do 37. Oh, all right, 41. We haven't learned that yet. Oh boy. Number 57, all. Let's do 57A and B. 57A and B. I will do C. Okay, so remind me on Tuesday, I'm going to go through C with you, but you guys do A and B. And 61. 67. Let's see, let's give you enough problems to keep you out of trouble, Avery. What do you think? All right, 69 and 73A. That'll be enough. Well, actually 75. All right, that covers all of the acids. So that's all the acid problems. So, other than that, do you guys have any questions at home? Oh, wow, 18 new messages.